So now this exercise and also the final one, 3.34, they are about the geometric aspects of linear maps. And I think it's quite worthwhile. So read what's given here. We are looking for a single matrix, a simple matrix, which defines a rotation in a plane through an angle of positive pi half. You know what it means officially? The plus sign, the positive sign, always means a rotation counterclockwise. That's what you are familiar with. Meanwhile, also when using complex numbers and so on. Okay, so we want to rotate all the position vectors about the origin by an angle of positive rectangular, no, yeah, a right angle. So I want to say a positive right angle, or even saying plus pi half. Okay, so that's what we want to do. And then also at the same time, all the points or the vector arrows, you know what I mean, should be moved to twice their original distance from the origin. So that's like you combine a rotation with a scaling. That's all it is. That's all it means, with a simple linear scaling. And then the hint is to use a composite transformation. Now, about some background. What you should know, or what you even must know to this end, is how to construct a rotation matrix in 2 dimensions. But this is quite easily, well, you might look up some books or tutorials. It's quite easy to derive. And the result is that such a matrix, which rotates all the vector space through one given angle, is always a matrix where the cosine and the sine of this angle are placed at the different elements of the matrix. Where on the diagonal you always have the cosine of this rotation angle, while on the other diagonal, you could say on the second diagonal, you have the sine here and the minus sign here. That's just a fact, and we can test it, of course. Okay, so if we use this angle of pi half, we just take the code. We all know that the cosine of pi half is 0 and the sine of pi half is 1. So we get a very nice simple matrix 0, minus 1, 1, 0. And now we can even test it very nicely. If you imagine what this is something like quite the opposite of a diagonal matrix, because only the second diagonal is filled. And also by this minus sign, it's something like exchanging the sign, which you perhaps know from building a rectangular vector. What I want to say is the following. If you imagine a vector with components, a 2D vector with components x, y, okay? So just test it, because in this exercise, it's not, it's just about building this matrix. I want to extend it a little bit now for demonstration purposes. If I take this matrix 0, minus 1, 1, 0, and apply it to any vector x, y, what do I get? And you can see that what I get easily is Vertex principle, okay? Rho times clump. 0 times x minus 1 times y, so I get sort of exchanged coordinates, but also with the minus sign here. And then second row, second column, second row, first column, 1 times x minus 0 times y. So this should be familiar, perhaps, because you remember always when in 2D there's a trick. If I want to construct a vector which is perpendicular to another, I just exchange the components and then I put a minus sign at one of them. And so that's it. So this is obviously a vector which is perpendicular to the original vector. You see? So we have just understood why this is absolutely correct, that this matrix makes a rotation of pi half. Of course, now we would have to check that it's really positive pi half and so on. But I think this is a nice demonstration, okay? So what do? We take this matrix and then we say the second step is to scale the whole vector space by a factor of 2. And that's simple because that's just 2 times the unit, 2 times the identity matrix, you know, like the unit matrix, yes. So 2 times our 1, 0, 0, 1 matrix results to this one, 2, 0, 0, 2. And now I combine these two matrices. It doesn't matter in this case in which order. This is for a special reason. In this case, actually, in this case, they are commutative with respect to the multiplication, but this is just for reasons of, well, for certain kinds of mappings are exchangeable and others are not. So it doesn't matter. I take this one times this one, and then again, Erteg principle, row times column. You see there's 0 times 2 plus minus 1 times 0, so that I get nothing, it's 0. And then this one times this one, 0 times 0 plus minus 1 times 2, so I get here my minus 2, and then second row, first column, 1 times 2 plus 0 times 0, so 2, and then again, second row, second column, 1 times 0 plus 0 times 2, which is 0. So in the end, it's easy. I could also just have said, after I made this rotation, I just take this matrix times 2, every element times 2, and that's what I get. So in the end, that's the matrix which makes this linear mapping. Okay, so that's quite nice, but also simple. And then since time is not yet over, so I would say let's just have a short look also at this one, which is now I see we even have 2 more exercises, right? This one is perhaps for your convenience, just to have a look by yourself, because it's relatively easy to understand. It's all rotation again. Better speaking, 2 rotations of it's the same rotation twice. Okay, so this is by a square. We mean a times a. It means this rotation is applied twice. Then there is a obviously a point reflection and it takes place, and then again twice this rotation, and then we should show that for certain reasons this means that all the image vectors are identical to their pre-images, so that the identity mapping is resulting. That's what you can do by yourself. This one is more interesting, especially if I add that we should discuss the equation that results from this mapping. So what is it? This seems to be obvious. Is the equation which defines a circle around the origin with a radius of 2. Okay, you know that this is always the squared radius, very famous circle equation, and this one should be scaled by a factor, but this time not with a single factor, but the x component should be scaled with a factor of 5, while the y component should be scaled with a factor of 2. So this is it's linear, but it's you could say a certain stretching of this circle so that its form changes. You may all guess what the result might be. The result is an ellipse, of course. It's an elliptic curve with certain dimensions, with certain measures, but that's the topic of this exercise. And so I think it's easy to guess that this matrix is what we need. This is like sort of the unit or identity matrix scaled by 5 in the first row, by 2 in the second. So that's exactly what we need. If we apply this to any pre-image vector, we get, you see what we get, row times column, we get 5 times x here and 2 times y. So that means the x component is scaled by a factor of 5, the y component is by a factor of y. So that's what we need. And I call this resulting vector, now I call it x prime. Okay, so please don't mix it up with first derivative or something. It's just a notation. And also, if I use x and y for the components, it's not so probably not so good, such a good idea to use y vector for the resulting. So I think that's quite okay. I call my pre-image vector x vector. It has components x and y, and the image vector is called x prime. Actually, also its first component would be called x prime without a vector sign, and the second one then y prime. Now the problem is, let's look at the components separately. And you see, what happens here is that the original x component is mapped to 5 times x, the y component to 2 times y, nothing special. But and now I call these x prime is 5x and y prime equals 2y. This is the mapping notation. This is the more like sort of, yeah, if you want, functional notation. Now, but the point is, what we really need to transform this equation is not this transformation, but the inverse transformation. And meanwhile, you've already learned about inverse matrices, but I may say in this case, it's quite simple. If this mapping if we want to make this mapping, how do you say, if we want to compensate, okay, this mapping to get the origin, to get the pre-image values back, it's quite obvious that this is the inverse operation we need. So this time we scale by 1/5 and by 1/2. And afterwards you will see that we are doing the right thing. Oh, now time is almost over. Okay. So, but you believe me that this is the inverse matrix to this one, which means, in other words, if I multiply these two matrices, I get the unit matrix, the identity matrix. So that's quite obvious. So let's just do it. Let's apply this inverse matrix to the image coordinates, to an image vector. And of course, what we get is this one here times our image vector 5x 2y. And so we get 1/5 times 5x, which is x again, and 1/2 times 2y, which is y again. So we get our pre-image vector. So now this time, 5x is mapped to x, 2y is mapped to y, and that means that the old coordinate x equals to 1/5 times the new one, x prime, and the old y is equal to 1/2 times y prime. So now you see why I'm doing this, because if we want to transform this valid equation, which describes a circle with a radius of 2, to a new equation, we have to replace these old coordinates x and y in a way that's given here. So this x must be replaced by the term 1/5 x prime. This y must be replaced by 1/2 times y prime, and then the whole thing works. I do this, okay? I replace x by x prime 5/5, and then y by y prime half. I put the whole thing in parentheses, then I must build a square. I could do it, I could remove the parentheses just for your interest, and I could even put this equation to fraction-free form. Then it's quite nicely 4 times x prime squared plus 25 times y prime squared equals 400. But this is actually not at all the standard form. Instead, I do the following. I rename coordinates. And now I hope this does not embarrass you. So I rename them because I want to have a valid new equation using x and y coordinates. And if I do so, I get x5 squared plus y1/2. Oh, squared, I missed here, squared, equals 4. And now, instead of doing this, I even divide this equation by 4. The reason is the so-called ellipse equation in its standard form is always this kind of equation with the right side equal to 1. And that's because you can then recognize that it describes all possible ellipses around the origin of the coordinate system with arbitrary measures, including all circles, and without rotation, I must say, without a rotation against the coordinate axis. This is the standard form of the ellipse equation for non-rotated ellipses. And then there's also, you see a close connection to Kepler's laws, if you remember, things like that, planetary orbits. And so it's quite interesting. But in the end, if I divide by 4, it's clear, 4 by 4 is 1. But here, please be careful, if I divide by 4, inside the parentheses, I just divide by 2, of course, because this square outside makes 2 squared equal to 4. So I think that's clear, okay? And also here, 2 gets 4. 2 times 2 is 4. If I divide by 4, inside the parentheses, I divide by 2. So that's it. That's the standard form. And now, if you're familiar with such ellipse equations, you will recognize that every time we have this standard form, we can extract the so-called semi-major axis and the so-called semi-minor axis, these two values, this is mostly denoted to be A and this one B, okay? And we can just extract them and say that the semi-major axis is 10 in this case, and the semi-minor axis must be equal to 4. And this is exactly what you see in this sketch here. And so this is, you could say, this is the sort of the proof that what we achieved here is scaling this is a little, the sketch is scaled quite small, in small measure, okay? You see that this could be, this would be a circle with a radius of 2 in my grid here. And it obviously has been stretched by a factor of 5 in the x direction, and it has been squished by a factor, not squished, also stretched by a factor of 2 in the y direction. So, now I have a problem because, and the result is that the semi-major axis of this ellipse is actually equal to 10, and the semi-minor axis is equal to 4. So it's quite okay. It's quite correct. And this is called an ellipse in principal axes form. We will have, if you prepare yourselves for our last topic before Christmas, which is eigenvalue problems, we will have this topic about principal axis form of so-called quadratic forms. And this will be an interesting topic about quadratic matrices of a special sort. So there's a connection between this topic and the other. So sorry for taking a little more time now, but I'm done, and you can you're welcome to ask some questions too.